So on the last tutorial, we talked about phase transitions, and what we saw is that it's very hard to, like, the type of systems that we look at. The problem is that it's very hard to actually get any real information, I think, on the system. Like you remember that if you notice that we only looked at order of magnitude of stuff. Like, oh, the energy is proportional to the number of particles or to the log of number of particles. Like, that's basically everything that we can say. So what we're going to do now is we're going to use some approximation such that we actually will be able to do something with the system. So the approximation that we're going to use is called mean field approximation. So basically what it means is that we have a system with spins, and each spin in the system is connected to any other spin in the system. So when we look at the interaction term, we have Si and Sj, and if usually we have nearest neighbors interaction in one-dimensional Ising model, or even next nearest interaction. So now we have for any I and j, for any I that's smaller than j. So this is basically any I and j in the system, any pair of I and j. And the small one is just so we won't count, we're not going to count twice the same interaction. So, and in addition to that, we have the usual magnetic field. So this is not going to change. And if we talked in the last tutorial about what happened in one-dimensional or two-dimensional or three-dimension, so mean field considered to be infinite dimension. So the reason is just the way the system behaves, but this is what it is. So this is the Hamiltonian, and basically what we're going to do now in the tutorial, I'm going to solve a question from some test, and then during the solution I'll show everything that you need to know. Yeah.
It's because we took the n to infinity, right?
You took n to infinity?
The number of
yeah, but you have an n go to infinity also in one dimension and two dimension.
Okay.
Here, because you have you connected to any other spin in the system, so it's like where you look at dimension of a system. If I have one dimension and I want to get from point 1 to point 2, I have to go through some trajectory. If I have 2 dimension, I have different trajectories that I can go, and it's defined the length of the trajectory. So when I increase the dimension, I can calculate it through the trajectories that I do, and when I connect all of the spins, I basically have infinite. The average trajectory will be infinite because I can either jump.
Okay. Yeah.
Let's not go too into details, but this is just
for infinite.
It doesn't really mean
from
anything.
One point to other points. From getting from one point to other point, we have infinite objects. That's
if you do a random process or something. People do something similar in random walk stuff.
Okay.
But it doesn't matter. From what we need to know, this is just the Hamiltonian, and that's what we need to solve. So basically so the question we are going to solve is from 2019. And basically the question is you have given a Hamiltonian that I'm going to write in a second. And you need to find the free energy. So find the free energy using saddle point approximation. So basically all of that type of questions we have in Hamiltonian, mean-field Hamiltonian, and we need to find the free energy, and in order to do that we need to do series of approximations and tricks to find explicit term for the free energy. So we're going to do it like step by step, and then in the end I will like summarize all of everything that we did. Okay, so the Hamiltonian is well, it's basically this Hamiltonian, and in the question they give that SI can be equal to plus minus 1 or plus minus 2. And this is like a weird version of Ising model. So, okay, so how do we start? So in order to find the free energy, we always start with the partition function, because that's what the way we always start to calculate stuff. So, so the partition function is defined in general as the trace of the exponents of E minus beta H. So, trick number 1, I guess. So, this Hamiltonian is going to be inside the trace. Now, the first part of the Hamiltonian, this summation, is not very convenient to do. Like, if you want to calculate the trace of that, I don't really know how to do that. So, what we're going to do is to take the sum of I smaller than j, Si, Sj, and to say that this is equal to, so this is basically summation over any I that's different than j. So this is equal to, so the first summation is any I and j in the system in general, including I equal to j. So there are two summations, minus the sum of I equal to j, which is, just write it as I Si squared. So this is Si Sj, where I equal to j. So the summation of I that's different than j is the summation of all I and j minus the summation of I equal to j. And we have a factor of half to not count twice the interaction like this, in the left hand side. Okay, so this is the first step, and you already see that this is a bit more, maybe you see, I don't know, this is a bit more convenient to work. So this I can write. So the first sum is basically the summation of I Si squared, because I don't have any, they're independent. I have a sum over I and a sum over j, and they're independent on each other. So I can just take one of the summation and take the square. So, and the first sum is, and then the second sum is the sum of I Si squared. So that's what we are left with. Okay, so now the partition function is equal to the trace of an exponent so I have okay, I have the first expression, I have beta j over 2 sum of Si square minus beta j over 2 Si square plus beta h sum of Si. Okay, so So now I have, okay, so if I want to calculate the trace of everything that I have inside the exponent, so those two are going to be quite easy, and if you don't see that, like we will do the trace later, so you will see why those are easy. But this one is still more complicated. Like I still cannot take the trace immediately. So we're going to use another trick. Transformation or trick, depend on. So it's called Hubbard Stratonovich. I hope I don't abuse the name. Hubbard Stratonovich transformation. So the transformation is basically that. So if you let's take a Gaussian integral just for fun. So we have an exponent of minus x squared over 2 plus bx plus c. This is equal to an exponent of b squared over 2 plus c. This is just Gaussian integral. So if we look at the right hand side versus the left hand side, so we see that here we have something that's go like b squared inside the exponent, and here we have something that's go like linear with b in the exponent. So I also have the integration here, so which makes it a bit more complicated, but still I go to something that's linear. So what I can do is I can define b squared over 2 as that. So this is beta j sum of si square, and I take c to equal basically all of that. So let's call that c. And if I do that, I can rewrite the exponent that I have here as an integral so x have nothing to do with what I have here, so I'm still going to have x plus bx. So we defined b like that, so what we're going to be left with is square root of beta j si x, and plus c, which is everything that we have here, so I'm just going to copy that. So basically we started with something that go like this parameter square, and we stay with we left with something that's linear with the same parameter. I think. Yeah, so okay, apologize. This is defined with j over n. Because we sum over all of the particles, so we usually put that for units. So I'm just going to go and correct that. So n. Questions so far? Okay, so now we can finally take the trace of the exponent. So we can change the order of the trace and the integration, because the integration is like a summation. So let's take the trace of what we have here. So I will write it. I write it in there. So we have trace of an exponent. We don't need to consider that, because this is just part of the integral. So I'm just going to take everything that depends on the state of the spin. So we have square root of beta j n si minus beta j square plus beta h si. So if you remember, I think we did in one of the previous tutorials, when you take the trace, you sum. So the summation inside the exponent is going to give multiplication of. If I take it outside of the exponent, it's going to give multiplication over all of the different particles. So I is go from 1 to n. And the trace is going to give me a summation over all of the different states of the spin, which we saw that we have 4 different states. So Si is equal to plus minus 1 or plus minus 2. So this is the just equivalent to write the trace. Then I have the exponent. Copy it again. So without the sum. Okay, so for each, so let's start with plus minus 1. So for both plus and minus, the term that include si square is not going to change, because plus and minus 1 is still 1. So I can take it outside. So I take e2 minus beta h over 2n multiplied by 1 for plus minus 1.
Beta j, right? Beta j.
Yeah, sorry. And then I have 2 terms for plus minus 1 for si, so this is e beta j n x plus h beta h plus e minus square root of beta j n x minus beta h.
Isn't it just cosh?
Yeah, it is. So this is 2 cosh and the same for plus minus 2. So this is going to be plus minus 2 beta j over n. So I have 2 squared to give me form, yeah. And then again I have for plus minus 2 the 2 exponents. So I'm going to get 2 cosh of 2 beta j n x plus 2 h beta h. So, okay, so after we did the summation, we need to do the multiplication. Now, everything that we have inside the bracket, it doesn't depend on the specific particle. It doesn't depend on the index I. So this multiplication from 1 to n just going to give me this expression to the power of n. So this is going to be e minus beta j. So all of that to the power n.
Now we need to integrate it.
Yes. Like yes, but no. So okay, so let's put everything back inside the trace. So I'm going to rewrite on that, so I won't have to copy that again. So z is equal to, we don't have the trace anymore, we have the integration, is e minus x squared over 2, because we still have this part, and then all of that.
The bounds are still from minus infinity to infinity?
Yeah. We didn't do anything yet to the integration. We are going to do something now. So, okay, so basically now we need to solve this integration, but we really don't want to. So what we're going to do is, so in the question they ask you to find the free energy using Southern point approximation. So we're going to talk about what Southern point approximation is. But before that, we're going to do a change of variables just to make the units more convenient. So, yeah, this is not like a trick or something that we necessarily need to do, but just later, when we find the free energy, we won't have to reorganize everything. So we just technically more convenient to do. So let's say that x is equal to some parameter y multiplied by the square root of beta j n. So I'm going to do that, and then later when we find the free energy, I will explain why I chose that change of variables. So now z is equal. So I have some constant here outside, but we're going to ignore it because it's going to cancel out in a minute. So dy, this is pi, not x, e to minus y squared beta j n over 2 So instead of the square multiplied by x, we're going to have y beta j just change of variable, nothing interesting. Okay, so now saddle point approximation. So I'm putting that aside for a second to talk about that, and then we're going to use it for the integral. So saddle point is like nekudat ukaf, you know. So basically, let's say we have an integral of a function that's go like have an exponent of a function of go like n f of x. So f of x can be I don't know, like this can be like a Gaussian or something. So f of x can be like a parabola. So let's say all of that is looking like something like that. Okay, and then the y of the function is determined by n. So if fx has a minimum point in x0, so then if I take n and I keep increasing it, so I take n go to infinity, this function going to be more and more narrow. So it's going to, so you can see, like I put a derivation in the tutorial in the model, so you can see it there. But basically, you can imagine it's just going to get more and more narrow. So most of the contribution to the integral going to come from this point here, which is x0. So that if the minimum of f of x is in x0, then the maximum of this exponent is going to be also in x0. And in that case, you can approximate this integral to be just e minus n f of x0. So this is like what happened in like a delta function, which like, you know, the extreme case. So basically you get it by taking the Taylor series of f of x, and then this will just give you the first order. So this is the saddle point approximation.
What if I have a number of saddle points?
If you have what?
If I have more than one saddle point.
You mean more than one minimum?
Yes.
It's called saddle point because you have saddle point in the complex plane. It's like a whole thing. But yeah, if you have more than one minimum, then this can give you like approximation in some area. But basically, if you have more than one minimum, this is a bit more complicated. So you can get like multiple contribution or something like that. But we don't do that here. Basically, it's going to be something like that. Okay, so we can rewrite, so this is what we got earlier, and we can rewrite that as, so instead of, I want to put everything here inside the exponent. So what I'm going to do, okay, I don't want to copy paste it again, so. I have an exponent, and then I just take the exponent of the ln, the logarithm of everything here. So I have n logarithm of all of that, and this is all inside the exponent. So instead of multiply, I take and I take the n outside of the log because that's how log works. So, okay, so now I have an integral of an exponent of a function, and this is already it's kind of similar to what we got here. So what's the free energy? So the free energy in general, if we want to calculate it from the partition function, so this is f, it's not, okay, I don't want to confuse with that f, but this is free energy. So the free energy is minus 1 over beta n, the log of z. So let's say all of that, everything that I have inside the exponent in the partition function, I call it nfy to be later consistent with what we did for the salad point, but for now this is just the definition. You see that I have n here and I have n here, so I can take n outside. So follow this definition, I'm going to get, so I have minus 1 over beta n, and then I take the log of this exponent, and I have minus n f y. So this is just f of y over beta. So that means that the free energy is basically up to a constant to beta, but I can define beta, I can just take beta out here the same as I did with n. But basically the free energy is just the function that I have inside the exponent here. So why is that important? Because we know that the free energy gets the minimum value where, well, physics happen. So the free energy always get the minimum value. So in that case, it would be the minimum value in respect to y. And that's going to be the minimum value in x0 that we have for the salad approximation. So it means that I can approximate that. I'm going to do that. I can approximate z as, instead of taking the integral, this is approximately just e minus n f of y0. So y0 is just, I'm going to define it in a minute, but it's whatever gives the minimum of the free energy. So this is like, if we looked at the trick, so this is like trick number, I don't know, 4. So this is the Southern approximation. So the moment we did that, we don't have the integral anymore, we just have this function, then we can calculate directly the free energy using this definition, like we basically did. So this is just equal to, so j y squared over 2 plus 1 over beta, none, and then, yeah, I'll copy it just so we have it organized, e minus beta j. So this is F. Okay, so basically this is the solution to the question. In the lecture you saw a video, I hope, or you will see, but I think you already saw it. that you can prove that y0 is actually the average magnetization. Like y0 is equal to this or this. You can call it whatever. So you actually get the free energy as function of the average magnetization M. So we usually call that order parameter. And we're going to talk in the next tutorial, we're going to talk about more basically phase transitions. We're going to talk more about this order parameter. But basically, if you have like, because it's the average magnetization, if the average magnetization go from 1 to 0, that's when you have the phase transition, right? When we have the simulation in the homework, so we had the average magnetization versus the temperature or something. So you had here finite magnetization, you had here zero magnetization. So this was the order parameter of the system. So what we're going to do, we're going to study how this order parameter behave in different types of systems. But this will be later. So this is the free energy, and we got it as function of the order parameter, and basically, as you saw, it's just a series of a little bit ugly calculations, but it's mostly technical. So
the y in free energy is y naught.
yeah, sorry, this is fine. So this is so in general it's something that relates to the magnetization, and because it's what minimizes the free energy, because that's how the free energy is defined, it's going to give us the order parameter. So okay, so what did we do? So there is a given Hamiltonian in the question. I'm going to solve another example in a minute, but basically what we did, the first step is to rewrite the Hamiltonian. So instead of going from SI, Sj, we go to SI square, SI square. The second trick that we did was to use the Hubbard-Stratonovich transformation. And then the third thing that we did was the standard approximation. Okay, and then we just find f using that. Question? Okay. So I have another example that's, I'm not going to go through all of the calculation because it's just very technical, but I have something that I want to show, so we're just going to go through it. So this is from 2015. So the question is the same question. The only difference is the Hamiltonian. So you have the mean field interaction, Si, Sj. but the external field is now divided into two different regimes. So you have the first one from all of the particles from I equal 1 to n over 2 magnetic field H1, and all of the second half of the particles going to feel a magnetic field H2. And SI is only equal to plus minus 1. So the main difference here is actually not just the magnetic field, but now when I'm going to rewrite the interaction term, so I have first SI square, so this is the same, minus SI square. So if SI only equal to plus minus 1, then SI square is always equal to 1. And therefore, this summation is just going to give me something that's just a constant that have nothing to do with the different states in the system. So this is just adding a constant to the Hamiltonian. So you can always add or take out constants from the Hamiltonian. So this is not going to change anything in the final result of the free energy. You can keep that and see that eventually it's going to cancel out if you really want. And that's why, which is actually what usually happens, because we usually have something that looks like that. Like the previous case that we saw was the exception. So this is usually going to cancel out, which is going to even simplify further the solution. So we're usually only going to stay with the first term. So now when we're going to write the partition function, we have j beta to n si square minus h1 minus h2
Shouldn't be h1 beta h2 beta.
Yeah, plus beta. We should take beta outside. So at that point, we do the same process that we did before. So one thing will be to do the Hubbard-Stratonovich. So we write that in the form of integration to get rid of the square. And the second step will be to do the change of variables. And eventually, when we do the trace, because we have this separation here between the two summations, so if I have so I'm going to do just this part, and again, this is like we did before, and I put the full solution on the model. But basically, if I have something that go like E H1 So now when I have the multiplication over n, I'm going to have, so I do first the summation of all of the spins from, okay, right. So, so I first do the summation of the different states of the spin, and when I do the multiplication, I'm going to have two different multiplications. Let's say one from I to n over 2, and one from n over 2 to n. But because I did them like separately, I'm going to get eventually. So this is, I'm going to write it as a cos. So beta h1 and beta h2, and all of that go to the power of n over 2 because I already did like 1 n over 2 when I separate those. So if they were like, if I had the same field, you see that I have only one of those terms to the power of n, but because I have the separation, I have this to the power of n over 2. So I hope that part is clear. And then everything else later is exactly like we did before. So I hope this was not too fast or something or too slow. Yes, because what happened is that you multiply n times, but you have different multiplication for that, and you have different multiplication for that. So you have so like this summation is I have n over 2 summations, and here I have n over 2. So when I take it out, I have like e to beta h1 si and e to beta h2 si, and this is going to go to n over 2, and this is going to go to n over 2. So if I put them together, and then if I would take h1 equal h2, I'm going to converge to the case that we saw before, that I only have that to the power n, because this is going to okay, so okay, so that was basically it. So okay, we went through it a bit fast. So if you have questions, that's the time. If you want me to go through some stuff a bit slower, you can let me know, either like now or like in general, because I don't really know if like, you know, sometimes it's too fast or too slow for people. So if you have feedback, that would be great.
For me, we're fine. For me, we're fine.
Okay, cool. So okay, if there are no more questions. Did you finish that with Vido? Because you didn't talk to me today.
We did those stuff.
Did you go to the question to the lecture?
Yes,
Yeah,
they
okay.
were there.
So you finished that?
Not exactly the
He
same.
told us we would not finish all the derivation, but I understood everything you did in the tutorial.
Okay.
We go to the y x now is the derivation, and then we did that same.
Yeah, okay, so basically.
Yeah, we're just saying I don't think you passed them.
I need to know what's the Okay.
Okay.
Yeah. כשאת אמרת כותבת את הטרייס בצורה כזאת יותר קטנה.
לא, אוקיי, אז הטרייס הוא... אז הטרייס הוא לא המכפלה, המכפלה מגיעה מהאקספוננט. אז כאילו, אוקיי, אז יש לי את הדבר הזה בעצם. אז יש שני שלבים שאני עושה. אז קודם כל הטרייס, הוא נותן לי בעצם את הסכום על כל המצבים האפשריים של SI.
אתה רוצה לעשות את מה שלא
במקרה הזה SI של 1.